In this chapter, several types of semiconductor devices are introduced. A family of devices known as thyristors are constructed of 4 semiconductor layers PN-PN. So if you don't know a PN junction by now, you have trouble. Alright, first one we're going to discuss on page 554, section 11.1, the 4-layer diode. You can mark the introductory paragraph there. The basic thyristor is a 4-layer device with 2 terminals, the anode and the cathode. It is constructed of 4 semiconductor layers that form a PN-PN structure. The device acts as a switch and remains off until the forward voltage reaches a certain value, then it turns on and conducts. Conduction continues until the current is reduced below a specified value. Although the 4-layer diode is seldom used in new designs, the principles form the basis of other thyristors that you will study. Right, we'll see that as we carry on with the next section as well. Alright, the 4-layer diode is also known as the Shockley diode or the SUS. And if we go and look at figure 11.1, there's a picture of what the 4-layer diode looks like. And as mentioned, then the 2 terminals, also called the anode and cathode, the same as we had with the diode that you've discussed in Electronics 1. Only in this case now I have 4 layers, PN-PN. And of course you also have to know the schematic symbol for a 4-layer diode, also known as Shockley diode or the SUS. Alright, how does this device work? What you should know is the 4-layer diode's characteristic curve on page 555. Let's have a look quickly at the characteristic curve, and please, if you are asked to draw this characteristic curve, remember that it must be fully labeled to get all the marks that you should get for the question. Alright, if I look at this characteristic curve, it's the anode current against the anode cathode voltage, VAK. And as you can look here, it is forward biased, and the forward voltage increases here from 0, and it will keep on increasing the voltage. I will keep on increasing the voltage until I reach this point, which will be called the forward breakover voltage. At this point, the device switches on, and you can see there that it starts to conduct current. Right, that current is called the switching current. That's at the moment that it remains on, and there's another current there that's called IH. That is the holding current. This device will remain on as long as the anode current is larger than the holding current. As soon as the anode current becomes lower than the holding current, the device switches off. Right, that's the basic operation, and you need to know the 4-layer diode's characteristic curve as well with its labeling. Alright, so now remember this characteristic curve that we looked at, because the other devices that we are going to discuss will be based on the same, and you will see, as we've said here, that all these devices basically works on the same principle. Alright, if I go back to figure 11.2, a 4-layer diode equivalent circuit. Remember we said PN-PN, and here you can see that I have a transistor equivalent circuit. The 2 transistors, there's, oops, just go back, PN junction 1. Let me draw that thing here quickly again. Remember 4 layers, anode, cathode, PN-PN, PN-PN. Right, here you can see then with the transistor equivalent circuit, PN junction number 1. There you go. Next one there, PN junction number 2, over there, and over here, PN junction number 3. Okay, 3 PN junctions, equivalent circuit for this device. Alright, so when a positive bias voltage is applied to the anode with respect to the cathode, as shown in figure 11.2b, the base emitter junctions of Q1 and Q2, PN junctions 1 and 3 in the figure 11a, are forward biased, and the common base collector junction, PN junction 2 in figure 2, is reverse biased. The currents in a 4-layer diode are shown in the equivalent circuit in figure 11.3. Right, there you can see the currents flowing there. At low bias levels, there is very little anode current, thus it is in the off state or in the forward blocking region. Alright, then the important part, as we've seen from the characteristic curve as well, which is discussed on page 555, is the forward breakover voltage. The operation of the 4-layer diode may seem unusual because when it is forward biased, it can essentially act as an open switch. There is a region of forward bias called the forward blocking region, in which the device has a very high forward resistance, ideally unopen, and it is in the off state. The forward blocking region exists from VAK is equal to 0 up to a value of VA called the forward breakover voltage, if you can recall from the characteristic curve that I've shown you. But we will have a look at it again. You just get there. Right, so as we've discussed here, there's the forward blocking region. So until this value is then reached, the forward breakover voltage, you can see then that the device switches on at the switching current, and the device will remain on as long as the current the anode current remains higher than the holding current. Anyway, at the bottom of page 555, they discuss the holding current as well, and the switching current. You can have a read through, and then at the next page on page 556, example 11.1, a certain 4-layer diode is biased in the forward blocking region with an anode to cathode voltage of 20 volts. Under this bias condition, the anode current is 1 microamp. Determine the resistance of the diode in the forward blocking region. Normal Ohm's law to do that calculation. So look at the other examples as well. Then an application at the bottom of page 556 is the relaxation oscillator, which is so we can see when this switch is closed, what is going to happen. Just get there, switch over there. When the switch is closed, the capacitor charges through R until it reaches the forward breakover voltage of the 4-layer diode. Okay. At this point, the diode switches into conduction, and the capacitor rapidly discharges through the diode. So we can see here from the curve. So it charges, and when it switches, discharges quickly. Discharging continues until the current through the diode falls below the holding value. At this point, the diode switches back to the off state, and the capacitor begins to charge again. The result of this action is a voltage waveform across C, which is shown here in figure B. Basic application of a 4-layer diode. Alright, that concludes then section 11.1, the 4-layer diode, as an introduction to chapter 11. And we will see that the other devices is also based on this basic theory that we have discussed here.